Hello, everybody. My name is Mingde Zheng. I am a biomedical scientist from Nokia Bell Labs, headquartered in New Jersey, USA. It's a pleasure for me and my colleague Salvatore and Bibek to share with you an exciting work that we are done in the space of wearable technologies, specifically a screen-printed bioelectrical sensing sleeve that is stretchable and capable of high-quality signal acquisition from the body surface. So the motivation of this work originates from the wide application and adaptation of human-machine interface, or HMI, from enabling prosthetics to augmenting human capabilities to controlling robots, machines, and devices, as well as daily digital interactions at a consumer level. The impact of HMI has been particularly obvious with the rise of Internet of Things applications, and we believe the demands for better, more natural, and seamless connectivity between us and the devices will only increase. So with that said, there are two key areas in development that we focus on bringing about a practical HMI wearable. One area hinges on the digitization of human nonverbal commands. For this, we have chosen the acquisition of bioelectric signals at the forearm in order to translate electrical impulse commands from the brain that activate both coarse and fine skeletal muscles for motions. The other area of development emphasizes on the reliable form factor that comfortably and accurately allow humans to interact with devices by solving some of the challenges facing current commercial equivalents, such as sensor bulkiness, inflexibility, and poor signal quality, and etc. To this end, our approach rests on four legs, developed in the form of accessory armband. This sleeve is practical in that it can be mounted and taken off easily. And at the most intimate level, the fabric we choose to be in contact with the human skin prioritizes comfort while still permitting customizability. It's made of nylon and lycra mixture to promote stretchable, breathability, and conformity. Instead of bulky wires and cables, we screen-printed highly conductive tracks interconnects to link all of the circuits and electrical pathways on top of the stretchable fabric. Through a carefully crafted protocol, robust and highly stretchable 2D traces can be made. In order to offload any hardware weights, we split our main hardware into 8 acquisition modules, with each implemented on a flexible PCB that weighs about a gram and measured at the size of a dime. In this manner, the weight is distributed and the user won't feel any discomfort of bulkiness and mechanical hindrance. Lastly, another aspect of this work rests on the microfluidic-wicking design of our electrodes used as biosignal transducing medium. Taking advantage of the wetness in gold standard gel-based electrodes to obtain high-quality signal, we utilized a multi-layered corrugation thin foam to wick and retain small amount of liquids on the body surface. These foams were made with highly conductive nanoparticles that they also have excellent vertical and horizontal electrical characteristics. Furthermore, depending on the skin condition, for subjects with higher surface hair density, a greater foam layers can provide the mechanical extension necessary to push aside surface hair and allowing surface contact. So putting together all implementation, we demonstrate this wearable sleeve's performance as a bioelectrical sensor through the acquisition of sEMG signals on the forearm. A series of 12 finger gestures were performed, and the plot on the right here shows a typical example of a fist gesture made 3 times from using either gel-based white electrodes or our quasi-dry electrodes. The quasi-dry electrodes perform comparatively to that of the white electrodes, but without a messy cleanup, uncomfortable sensation, and potential skin reactions. With one pass of the moist wipe, our user did not feel any feeling of wetness, but the signal-to-noise ratio obtained across each channel for all gestures remained to be comparable. This is also true for subjects with dense hair, surface hair as well. So in conclusion, we demonstrated a sleeve accessory for bioelectrical sensing applications with comfortable and stretchable fabric and lightweight and hardware to allow the acquisition of bioelectric signals from the forearm at gel-based electrical quality. We have created a framework for developing any type of contact-based sensing systems, and the methods for fabrication can be easily adopted for further scaled up in improvement. Thank you for your attention.